Hello. I'm going to talk about anomaly detection and robotics. I'm a PhD student at IDSIA, the Istituto dalle Molle di Studi sull'Intelligenza Artificiale in Lugano, in collaboration with both USI, Università della Svizzera Italiana, and SUPSI, Scuola Universitaria Professionale della Svizzera Italiana. But before getting into my PhD, I was an Italian student at Bicocca, where I got into a double degree with the Università della Svizzera Italiana, and I did my master degree both in Bicocca and in Lugano. But let's get back to my presentation. Today, I'm going to talk about anomalies, as I said before, and robots. So more and more robots are around us and are solving different kind of tasks with different kind of autonomy. For example, we have delivery drones in the US, like those from Amazon Prime, that can deliver packages from the dispatch center directly to houses, like this is in the video here. Or we can have self-driving cars with different level of autonomies. Here we have a Tesla that is driving by itself around the country. Or in other cases, we can have different kinds of robots like Spot from Boston Dynamics that can interact with the world with different degree of autonomy. It can automate itself going around the room, or it can simply follow human commands, but integrating some autonomy, for example, for handling the legs or handling the arm. What all of these robots have in common is that while they are being developed, they are usually built and designed to deal with some kind of problematics that they can encounter in the real world. But then when they are deployed in real world scenarios, they usually end up in unknown environments, and unknown environments mean hazards, because in unknown environments, we can expect unexpected situations, and this can be hazardous, and in the end, can be highly costly. In these two examples that are kind of funny, we can see on the left side a self-driving car that doesn't understand that there is a van parked on the wrong side of the road and act on the brakes too late. And on the right side, we have a even major fail of a almost self-driving drone, something like that, that fails to recognize the pilot and goes into the face of the pilot. So these two cases are pretty extreme, where the robot fails a lot and actually creates some high costly damage, like to the van and the car and to the pilot. But in general, problems related to autonomous robots that, since they are not designed to detect strange situations, they can fail and simply abort the mission, or they can destroy and create damages. So our objective right now is to detect anomalies before they become an hazard. We can go as researcher to nature and see what nature does. And both us, human and animals, have evolved a behavior that it's called neophobia. This is the avoidance of objects and other aspects of the environment, just because they are different from what we have experienced before. This allows, for example, an animal to stop before something strange happens when it detects something strange. As an example, the dog of my supervisor once was going around in a park trail, and it started to bark to a tree that was fell down on the road, just because it never seen a tree horizontal instead of sitting upright. So while talking about anomalies with my supervisor, I was thinking about what is an anomaly for us. Well, a tree that has fallen down on a road, it could be understandable by humans. But then I was thinking about Inception, and this scene in Inception movie. In that movie, the world around the characters start to fold on itself, and that's something that I think any one of us would stop and think, okay, that's something strange. That's an anomaly in real world. If that would happen, so for us, an anomaly could be something that is real extreme, like that from Inception. But for in a general meaning, an anomaly is something that get out of a normal context. So we have a normal concept of normality, and then we have a sample that spikes out and gets out of the normal concept. So in this case, we have a simple example of a temperature sensor that detects that the temperature of a room, and for some seconds the sensor gets us a high temperature, and that's probably an anomaly with the sensor itself. It's not that the room caught on fire and then put itself out. It's simply that probably we have a problem with the sensors. But this is a simple anomaly. Well, for robots, usually anomalies are a bit more different. For example, they could be defects that cannot be detected by normal sensors. Let's imagine that we have a robot that somehow gets damaged and the camera starts to point upwards instead of horizontally. Then that would be an anomaly. Or could be environmental anomalies like water condensation. This is coming from a real world project that I'm working on. In that case, we have a drone that is flying inside aqueduct tunnels. And in these tunnels that can be long, multiple kilometers, water can condense upon the ceiling. And then whenever the drone passes through that tunnel, the draft from the rotors of the drone can move the water that is sitting on the ceiling and provoke an immediate shower that destroyed the drone maybe 1 or 2 kilometers into the tunnel. So it's also cannot retrievable. Another type of anomalies could be something that can be expected even for cars, like debris. Let's imagine that we have a wheeled robot that has to traverse a corridor, and at a certain point, it detects some debris like screws or nails. If the system was not designed to detect this small object, it could go over them and maybe puncture a wheel. And then another kind of anomaly that is coming from a real project is, again, dust. This is coming from the same drone project that I've been working on. In this case, dust is attracted to the drone due to some static electricity, and it can build up on the propellers or way down on the drone and in the end crash it. So we have to detect different kinds of problems that are all different from one another. And so we imagined a scenario of a wheeled robot that goes around an empty corridor, and whenever the corridor is empty, it's fine, the robot is happy and everything is okay. But then at a certain point, something happens, something is detected, something is in front of the robot or near the robot, and we want to identify that something. How can we do that? Well, what we usually do in research, at least in robotics and in intelligent robotics in specific, is go and look for machine learning or deep learning solutions. And one standard solution is supervised classification. What you can do in supervised classification is to gather enough information from both normal and anomalous samples, create a training set, and train a model. Then you take that model and you apply it in the real world. In the real world, that model will give us information from the blue squares and say that those are safe because those that was the ground truth that we passed to the model. And for the green squares, it would say that those are unsafe. But what if we encounter something that was never in the training set? Then the model would be unsure of the prediction that it would spit out. And in this case, it was an anomalous sample, so we would have a problem. Where the supervised classification approach fails is that gathering anomalies in the field is really difficult, since anomalies are rare and unexpected events. And even when you gather enough information, those are not a representative of future anomalies. And remember that if we don't get this right, the consequences can be very costly, like in this funny GIF that I've found. About anomaly detection. So the solution that we have found is anomaly detection, or also known as auto-distribution detection. In this case, we don't care about collecting data that it's also anomalous. We only collect normal samples, and that's our training set. We train a model just to detect and learn about normal situation. And then in the real world, we say to the model, okay, give us an anomaly score that it's 0 if you are seeing safe samples, or 1 if it's an unsafe sample. And what we expect is that for blue squares in this simple example, the model have to give us a low anomaly score, and for anomalous samples like the green and gray box, it has to give us a high anomaly score. So in order to do so, we had to record data. So we recorded data from a simulated tunnel and a real factory. I have to skip it because it's a bit long, this video. So in this case, we are flying a drone in a factory and we are recording normal samples and some kind of anomalies. And we also drove a wheeled robot inside our university corridors to gather enough information to train this kind of systems. This is also a data set that we are publishing in a future publication. And then what we can do is to take a deep learning model and use it to train the anomaly detection system. The deep learning model that I'm first going to talk about is a reconstructive neural network. In this case, the reconstructive neural network is an autoencoder. And the autoencoder, I don't know if your knowledge on this kind of networks, but it's built of three main parts. We have an encoder on the left side that take an image as input, compress that image into a lower dimensional, higher semantic information. And then we have a bottleneck that is here, the central bit. This part is very essential because, first of all, it flattens the embedded information into a one-dimension vector that loses all the spatial information that was kept by the encoder. And then it reduces the size from a high-dimensional, a large vector to a smaller one. And this introduces an error in compression. And we exploit that error in compression in the decoder that takes this information and builds up the image that it has taken as input. But while doing so, it makes an error, and we exploit that one so we can do a difference between the original image and the reproduced one, and we get an error map. In this case, the error is highlighted in yellow, while the correctly reproduced pixels are darker. And we can exploit this error map because this reproduction error that we impose is low for normal sample, but is high for anomalous samples. So we can gather information. Again, we took a smaller data set during one of the first lockdowns. This is a corridor in my house, in my apartment, and I was driving around with the robot, and an empty corridor, it's an okay corridor. So we have a small reproduction error in the output of the autoencoder, that is the bottom image here. And as you can see, the amount of error is limited to some distance details. But then what if we put something inside that corridor, for example, my cat or some bottles? As we can see, the model, since it has always seen not only normal samples, cannot reproduce correctly or at all the anomalous objects. And it introduces a lot of error in the reproduction that we can exploit to get an anomaly score. So this is one of the two approaches that we are using. The other one is actually a bit more complex, but it's based on the same autoencoder, and it's called density estimation and using normalizing flow. Normalizing flows are a kind of neural networks that make a mapping between a data space, that is what we give to the network, into a latent space that is a space that we like because, for example, there we have a nice imposed Gaussian distribution that we can interact with. So in this case, we have an example of a normalizing flow that takes the 2-moon dataset and maps it to a bivariate Gaussian distribution. And in addition, these models allows you to sample from this distribution and gather new samples into the data space. How can we use this? Well, we have a simplified autoencoder here that takes an image and compress it into a reproduced image. We do not care about the reproduced image. We take the embedding and use it as a data space origin. And we take the space of the embeddings that the autoencoder reproduced, and we map it through the normalizing flow. In our case, we are using real MVP, a kind of normalizing flow, into a nice Gaussian multivariate distribution where we can do nice statistic and probabilistic analysis and detect if an anomaly, a sample is anomalous or not. So in the end, anomaly detection is the neophobia for robots. It allows us through the use of deep learning to detect anomalies and help us to detect all those other situations that were not thought of during design time of robots. But does it really work? Well, yes. First of all, we have a video that we had made during the first lockdown. In this case, my wife is going to throw a pillow in front of the robot. And since the pillow was never seen by the robot, we coded the robot to turn red and to stop and do not respond to controls. I'm here controlling the robot in the background. And until the anomaly is taken away from the robot, I cannot control the robot. As soon as the anomaly is taken away, I get control again of the robot. But we also were able to bring this approach to more complex systems. In this case, we have a Sentinel drone anticipating another drone. You can see the outside view of the two drones. Here we have the Sentinel, here we have the Precious drone. We are going further in this case because we are not simply detecting the anomaly, but we are also acting a policy. The policy is to backtrack as soon as the anomaly is detected. I will go back a bit. This is the image coming from the drone, and this is the output image from the autoencoder, and this is the difference. And as soon as the average anomaly score along some frames surpass a certain threshold, the anomaly detection system is triggered and the policy to backtrack to safety is started. So in this case, you will see that some tape that is stretched between a pillar and a door is detected, and the anomaly system says, okay, it's better to go home, otherwise we can get damaged. So that was it for me. My final message is that hazard detection for robot is necessary, it's hard, but it's also solvable. Thank you for listening.